Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Process Stack Behind the Curtain. Well, today we will have a quick recap of the process logical address space first. Then we will talk about the command line arguments and environment variables. We will discuss in detail layout of a process user stack, growing and shrinking of the stack, and the buffer overflow. And finally, I will close after the discussion of non-local goto using the long jump. Let's start playing. Okay, before I start discussing the detailed layout of a process stack, let me have a quick recap of the 32-bit process logical address space. Let me start with the lower addresses which are at the bottom to the higher addresses which are at the top. Well, the program entry address is 8048.000 hex, where we have the .init, .text and the read-only data. There is a system variable eText that points to the first address above the code section. And above the code section we have the data section, which is divided into two parts. First we have the initialized data section, and the system variable eData points to the first address above the initialized data section. After initialized data section we have the uninitialized data section or BSS, and the system variable end points to the first address above the BSS section. And of course you know that these two portions are loaded from the executable file. Well, after the data section we have the area of memory that is reserved for heap, and the system variable brk points to the top of the heap at all times. Well, dear students, when your C program starts, both the brk as well as this end variable points to the same address. Okay, let me move on to the top now. Over here, this area is reserved for the kernel code and its own data structure. Almost 1/4 of the process address space is reserved for this, and it is invisible to the user code. Below this, starting from address BFFFF, we have the user stack or the process stack. And of course, in today's session, we are going to dig out details of the layout of this stack. Let us now move on to the terminal and see a program to understand the memory layout of a process in detail. Let me vim a program logical addresses. Okay, so I am declaring the external variable etext edata end. Then we have I, which is an initialized global variable, and j, which is an uninitialized global variable above the main. This I and II are stack variables. Then I am printing the page size of my system using the get page size. Then I am printing the address of main and eText. Then I am printing the address of the initialized global variable I and the initialized global variable j along with edata and end. Then I am requesting the system to allocate memory inside the heap for one integer variable, and I am printing that address as well. And finally I am displaying the address of the three variables which are there on stack, that is argc, I and II. Let me compile and run this program. Well, you can see the page size is 4 KB, and this address of main is, of course, this is below the eText. This is the address of the initialized variable, and of course this is below edata. This is the address of the uninitialized variable, and of course this is below end. So this proves whatever I have said about etext, edata and end. Well, this is the address of heap, which is above the end variable, and these three are the addresses of argc, I and II, which are on the stack. Well, since this is a 64-bit machine, so it displays 48-bit linear addresses, and of course can be translated to physical addresses using paged segmentation scheme. Some of you might have studied this in the operating system course. Let me run this program again. You can note that all these addresses are same as above over here. However, the addresses on the stack are different. In this run, the address of argc is 3bfc and over here it is fb2c. Let me run it again. argc address is fb2c and over here it is e96c. Well, this is because most of the modern operating systems perform the address space randomization for the stack, and this is for the security reasons. Let me disable this address space randomization doing the command echo. Let me write echo to a file which is there in the proc directory, sys directory, the kernel directory, and the name of the file is randomize vspace. Says permissions denied, so let me do it with sudo super user do, and let me run the program again now, and let me run it again now. You can see the addresses for the stack as well now are same. For argc e1dc, e1dc, for I it is e1ec, for I it is e1ec. Well, dear students, it is not recommended to disable address space randomization. I will dig out to the details of this in our security module, inshallah. Let me move back. Okay, let's talk about command line arguments and environment variables now. Well, this code is a very basic code that displays all the command line arguments that are passed to main via two variables, argc, which contains the number of command line arguments, and argv, which is a pointer to array of character pointers. And I run a loop till null and display the values. Very simple. If I run this program like this, the memory layout of the command line arguments and environment variables are something like this. 1, 2, 3, 4, 5, 6. argc will contain 6, and argv sub 0 will contain ./myexe terminated with null. argv sub 1 will contain learning, then 2 is then fun with Arif, and finally we have a null over here. So this loop will successfully displays all these command line arguments passed. Okay, what is the use of command line arguments? Most of you might have used this command cat etc passwd, and its layout of command line arguments is something like this. The cat program is basically pass the file name as the command line arguments over here. It opens the file, reads its contents, and display them on stdout. So whatever command line is passed to cat treats it as a file name, opens it if it has permissions of course, and displays its contents on the standard output. Similarly over here, ls-l/bin, the ls program is passed these arguments. -l is going to change the behavior of ls, and it will display its contents in the long listing, and this is the directory which will be opened by the ls program, and its contents will be displayed in a long listing on the screen. Now the question is why the program name is also passed to the process. Why this over here argv sub 0 contains cat, and over here argv sub 0 contains ls. Why this program name is passed? Well, dear students, the reason is we can create an executable of a program with multiple names, and we can code that program in such a way that it behaves differently when called with different names. Let me move on to the terminal and show this with an example. Let me do cat to a program command argument example2.c. Over here you can see that the main is passed arg v sub 0. Okay, if this program is called with the name ./hello, it will execute this code, and otherwise it will execute this code. Let me compile this program with the name of hello, and let me compile this program with the name of bye. Let me call it with hello, and let me call it with bye. You can see the behavior of the program is different. So this is one of the usage of passing the program name as the command line argument. And now we know about the command line arguments. Let us discuss about the environment variables as well. Well, dear students, the way we personalize our computers running Microsoft Windows by setting the desktop background, the screensaver, and setting our default browser from Internet Explorer to maybe Google Chrome and so on. Similarly, all Unix-based systems let their users store their preferences in a set of variables called environment variables. Every user on a Unix-based system has a unique username, a home directory, a present working directory, terminal type, time zone, default shell, path variable, default editor, and so on. All these preferences are recorded in environment variables. And you can see the value of these variables by the env command. You can see this is a known variable shell, this is the log name, and this is path, this is his size. You can always use the set command to display the environment variables. You can see the environment variables are being listed with the variable name is equal to value in this format. You can see this home variable containing home Arif, the host name variable containing Kali, the language containing enus utf. Okay, let us customize them temporarily by changing the value. Let us change the value of his size. Let me first check out the value of the variable his size. Its value is 1000. Let me change it to 250. HISTSIZE to 250. And let me repeat the above command, and you can see the value is changed. Well, of course, you know his size is a variable that contains the count of the last commands which must be saved inside the memory. If you give the history command, it shows you all these values. And right now, if I use history wc, you can see it is showing 250 now because I have changed it. If you want to change it permanently, you can change its value in the .bash rc file in a user home directory for a specific user, or maybe in @c profile file for all the users of this system. Well, whenever you execute a program or command from the shell, a copy of these environment variables is passed to that program for proper execution. Let me use man environ as well. Well, this is a variable that points to an array of pointers to strings called the environment variables to read this man page at the time of your ease. Now, we know how to access, modify these environment variables on the shell. Let us do the same from within a program. Okay. Well, this slide shows a C program that reads all the environment variables passed to it by the shell and display them on the standard output. it is using the external variable environ. And remember, uh, we can always pass the third argument to main, that is character pointer environ or envp, and use that variable instead of environ. But ANSI standard doesn't recommend this, and it recommends to use the external variable environ. So when we run this program like this, it will display all these variables on the std out, and some of them I have shown over here. Okay, the way we can change environment variables on the shell, we can also change them from within a C program using the put env and the set env function. Well, this get env function is used to access the value of a specific variable given over here. Unset env is used to remove the definition of a specific variable, while this clear env is used to erase the entire environment and then rebuild it with the selected values. Why on God's earth we need to modify the environment variables? Well, there are two reasons. One is to build a suitable environment for our process to run, and the other is a form of inter-process communication. Since a child gets a copy of its parent's environment variable at the time it is created. Let us move on to the terminal and see an example. And before I show you the code of the example, let me do man get env, used to get a value of a specific environment variable. Man put env, used to change or add an environment variable. Set env is more powerful than put env. This is also used to change the value. Over here we have three arguments. This overwrite argument, if it is 0, then the value of the name is not changed if it already exists, and if it is 1, it will overwrite it. Do read the man page. Man unset env, used to unset the specific environment variable. Clear env, and this is used to clear the entire environment, all the environment variables. Let me vim env ex3.c. Okay, over here I am using get env to get the value of his size, which will be stored in this value, in this variable, and it will be displayed. Then I'm using put env to change this value to 500, and that get env will print that value. And then I'm using set env to get the value of his size to 300, and this one means overwrite it. So this is a simple program. Let me compile it. You can see the original value of his size is 250, which I set it just temporarily before, and then I've changed it to 500, and then I have changed it using setjmp to 300. Okay, let us move back to this, and now we are going to talk about the process stack. We have a fair idea about the command line arguments as well as environment variables, and we know how they are passed to the process. Let's discuss the layout of the stack and how it grows and shrinks as functions are called and returns. Well, dear students, this slide shows the upper portion of the process stack. The upper portion of the process stack using the three variables argc, argv, and envp. And below this we have the stack frame of main and maybe other functions which are called later on. You can note the address is bffff. The stack starts from here. Well, this argc is an integer variable containing the number of arguments passed to main. This argv is pointing to argv sub 0, argv sub 1, argv sub 2, and so on to argv sub argc. So this argv points to null terminated strings over here, the command line arguments. And this is the third variable envp, which if passed through the main points to envp sub 0, envp sub 1 and so on to envp sub n, which is null of course over here. ANSI C standard says if you want to access the environment variables, instead of using envp, you should use the external variable environ, and we have used it to access them. Well, remember, dear students, stack grows from high to lower addresses in Intel as well as MIPS, Motorola and SPARC architectures. So the stack will grow down from here. Okay, well, when the main function whose FSF is over here, above the main function, this gray area shows you the command line arguments and environment variables. The main function grows from here downward. When the main function begins executing, the process stack contains only one function stack frame, also called the activation record, and that is of the main function, which is shown over here. The activation record of main function is used to, rather every activation record of any function is used to store four things. The first is the local variables, the other is the function arguments that are passed to that function, then is the return address, and finally the base pointer. And remember, these two registers, CPU registers, play an important role, play an important part in the manipulation of the process stack. This RBP base pointer points to the start of this function stack frame, and this RSP points to the top of this stack right now. And we all know that the stack grows down. Let me move ahead. Okay, function calling convention. You might have come across this word many a times. What does this actually means? Function calling convention means how function arguments are passed. Either they are passed via stack or registers, or maybe the mixture of the two. The order in which function arguments are passed, right to left or left to right. Who is responsible for creating the function stack frame, the callee or the caller? And finally, who is responsible for unwinding the stack, the callee or the caller? Well, there are different calling conventions that are used by C language, and these are some of these are the C declaration, the standard call, and the fast call. Please do Google to find out these conventions, details of these conventions. Well, this slide shows the idea of how a stack grows and how a stack shrinks. You can see if this is the FSF of main, and if main calls another function foo, the sequence of steps of creation is, first of all, the arguments are pushed on the stack in reverse order over here. Then the contents of the instruction pointer, that is the return address, is also pushed onto the stack. And then the contents of base pointer, RBP, that containing the starting address of the main stack frame, is saved on over here for later use. And this RBP is moved from this place to this place. So the address of this place is pushed over here, and RBP is moved to this place. Finally, this RSP is moved ahead so that the memory for the local variables of the foo function is created. Let's move ahead. So this is a concrete example. Over here, the main function is calling foo with 3 arguments, 2, 3, 4. You can see these are pushed on the stack in reverse order. Then we have the instruction pointer, the base pointer, and these are the local variables of this function xx, yy, zz, and so on. And this base pointer is pointing to the start, and the SP is pointing to the top of the stack. Okay, this is how the stack grows and shrinks. Okay. After the foo function returns, the memory on this stack is automatically freed. You can see that this RSP will be moved to here and RBP will move to here. So this is how the stack automatically grows and shrinks. So that is why all the variables on the stack are called the automatic variables. Okay, so now you know about the stack. Let me talk about another concept quickly, that is buffer overflow. Well, dear students, a buffer overflow is a bug in your program which occurs when more data is written to a block of memory than it can handle. Let's move on to the slides and see a program that has a buffer overflow bug in it. Okay, so this is the main function. If the main function receives no command line arguments, it will print no command line arguments received and it will exit. And if it receives one or more command line arguments, it passes the first argument to the display function over here. This display function receives the argument, copies it in its local variable buff, and then displays it on screen. It's a simple program. Let's compile and run this program. Let me pass it Arif. Well, the command line receive is Arif. Let me call it with Arif but. It works fine. And let me say learning is fun with Arif. So it gives you a segmentation fault. So what is the problem? Let me get it again. Well, the problem is we have a buffer of size 10 over here, and the user is providing more characters. Therefore, the program crashes. This strcpy is copying the characters from str to this buff, and if str contains, let's suppose, more than 10, over here 18 characters, it will crash the program. If you will enter 17 characters, it will not crash. Let me do that. Let me pass 17 characters only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it has not crashed. Let me pass 18 characters, so it will crash. We have created a buffer of 10 and it is crashing on 18th character. Why? Let me move on to the slides and understand this. Okay. So the main function is calling display with arg v sub 1. The display function is creating a buffer of 10, copying str to buff and printing the data. So this is the code. Let's see the stack. This is the FSF or function stack frame, or the activation record of the display function. First of all, these are the local arguments. This is a pointer, which is of course pointing to the string which is there in the constant pool of data. Then we have the return address. This is the address where this function will fall back to the main function. Then we have the saved RBP, that is this address is saved over here so that we can move the RBP to this place. Then we have a buffer of 10 characters. If we write Arif, ARIF, it will work fine. If we will write more data on it, this data is written from bottom to upwards, and finally it will overwrite this return address. And when it will overwrite this return address and this display function tries to return, it will try to return to this return address, which will of course not be the place over here in the code section. it will be an address of some random location that might not be containing executable code. So that is the reason you are getting a segmentation fault over here. Let me correct this problem as a simple application programmer. So it is always better to use strncpy instead of strcpy. Let me write down the count of the characters to be written. And let me run it again with this value. You see, it will just display that much number of characters which are now copied over here. strncpy will copy only 9 characters and then the null. I will do, of course, a scuba diving into this in our security module. Right now, I think that is enough for the basic understanding of buffer overflow. Okay, let me move back. Non-local goto. Well, dear students, this is the last part of today's session. Although not recommended, but you might have used C's goto statements to jump from one instruction to another. However, using goto statement, it is not possible to jump out from the current function to another function. And this can be performed using a long jump. And this is what we are going to do now. So let's straight away move on to the terminal and see this practically. And before I do a long jump, let me do a short jump. And I have done it in the program goto1.c. Well, I have defined two labels, label 1 and label 2. Over here I am saying that if the counter contains 6, then go to label 2 over here. Otherwise, I need to go to label 1 over here. So this seems to be like a loop which will print this string how many times? Yes, you're right, 5 times. Let's check this out. GCC goto1.c. Okay, it has printed 1, 2, 3, 4, 5 times. Okay, fine. So this is the only function main in which I have created 2 labels, and I can from anywhere in the code I can jump to any of these labels. Let me try to do a long jump using goto. Goto2. This is another example. Well, over here I have this main function. This main function is printing that I am in main, then it is calling f1, and in f1 I have a label, and then f1 is calling f2, and in f2 I am printing something, and I am saying go to label. From f2 I am trying to go to a label which is there in f1. So this is what is known as a long jump. Let me compile this program, and it says error label used but not defined. Okay, so why on God's earth we need to do a long jump? Well, consider a scenario in which during a deep nested function call we encounter an error, and we know that that error is handled inside the main function, suppose. So instead of every function returning the error value to its caller and to its caller and to its caller and so on to finally main, why not to have a long jump directly to the main function? So this is the need of the long jump. We have 2 functions, setjmp and longjmp, that provide this functionality. Let us see their man page. Well, this is the setjump function. The setjump function, when called, saves various information about the calling environment into this variable env of type jump buff. That is, it establishes our target for a later jump that is performed by long jump. And whenever we want to go back to the same state of the stack that is saved over here, where setjmp is called, we call long jump. And long jump is passed two arguments. First is this variable, and the second is an integer value. So this setjump is a function that is called once but returned twice. First it returns 0 when it is called for the first time, and the next time it returns only when we call long jump, and it returns with this value which is mentioned over here. So when you make a long jump to this env with this value, this setjump returns again. Do read the description of these two function calls. Let me move straight away to an example which can describe this. Remember, gentlemen, these code snippets are available on my Bitbucket account. Need not to worry, you can just go there and download them. Let me cat setjump1.c. Okay, so what I'm doing over here is I'm just printing this is main function. Okay, fine. This is the place where I'm calling setjump. So once this will be called, the state of the stack, whatever it is, it will be saved in this variable, and this will return 0 for the first time. So 0 will be compared with 0, and this line will be printed, and then this function will be called. And in this function, I will print this is a function, and then I will perform a long jump. I will perform a long jump to this variable with a value of 52. So this will fall back to this place again. But this time this setjump will return 52 in variable I. So this will become false. So it will, instead of going into this part of the code, it will go to this part of the code. And it will say, this is main again, value of I is 52. Okay. Let me compile setjump1.c ./a.out. Okay, so you see, let me run this code. So this is main, this line is printed. Setjump will return 0, 0 equals 0, true. So value of I is 0. This is printed over here. Then this function is called, and inside this function I will print this is function fun. Then I will do a long jump with value of 52, and this will fall back over here with the value of 52 in I. So 52 is equals 0. This is false, so this will not be printed. The control will come over here. This is main. You can see this is main again, and the value of I is 52. Okay, dear students. Now you know how to do a long jump. Please practice it and try breaking the world record by using long jump, as you may find a question on this in the exam. Let me move back to the slides. Okay, so that's it, the end of today's session. Dear students, do practice the concepts by running the code snippets and making minor modifications to them. It will be fun. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best, happy learning, and Allah Hafiz.